Hi everybody, welcome to our webinar. I'm going to start up with this content in just about 1 minute. Okay, let's get going here. Thanks for joining everybody. This is Chris Cowan with Ozen Engineering. Today we're going to be speaking about indirect electrostatic discharge analysis with HFSS. Our presenter will be Stephen Anchong Liu. I'll take a moment here to introduce Ozen Engineering first. We're a company that's focused on simulation. We use finite element analysis and computational fluid dynamics, and we're focused on high frequency and low frequency electromagnetic applications. We are a ANSYS Elite Channel Partner, and most recently selected as the ANSYS Channel Partner of the Year for the Americas. So we're proud of that. As a channel partner, we sell ANSYS software, we give technical support for our customers, we do training classes, and we provide consulting services if you have a problem that you need an answer to and you don't have the technical resources or the software capabilities to do that. We'll be happy to speak with you about how we can help you with that. We can also transfer files to you so that you can carry on your own. We deal with the full suite of ANSYS simulation tools, including structures, fluids, electronics, semiconductor embedded, and most of those are enabled to cooperate and work together for multi-physics solutions. We do a webinar every Wednesday or every second Wednesday, depending on the week. You can see here a list of recently completed webinars and upcoming webinars. If you're interested in staying aware of the upcoming webinars, you can register on our website under ozeninc.com/training. You can register for our newsletter, and we will send you a monthly update about the upcoming webinars that you can follow the links to register. And you can see our list of previously completed webinars. The recordings of these are all available on our website for you to access under Resources Webinar Library. One thing I'll say is that ANSYS has introduced a new product called ANSYS Cloud. The benefit to ANSYS users is that this provides easy burst solve capabilities. If you have a model but you don't have the compute resources to solve it either based on size or speed requirements, you can use the ANSYS Cloud that's implemented natively within the applications mechanical, FLUENT, and the electronics applications Maxwell and HFSS. So if you're interested in that, let us know and we can get you a 30-day trial of that. How do you contact us? You can email info@ozeninc.com, you can call us directly, or you can check us out on our website. One thing I'll add right now also is that we are currently looking for electrical and mechanical engineers. If you have experience in digital twins or embedded systems, we're particularly interested in speaking with you, so please get a hold of us. Now our speaker, Anchong Stephen Liu. If you're a customer of ours, you're familiar speaking with him about technical support for our electronics products. Anchong has a BS in electrical engineering from the University of California at Santa Barbara, and he is our expert in electronics application suite, so Maxwell, HFSS, SI Wave, and Simplorer. And most recently, Anchong's been doing a lot of work on digital twin applications, and we'll be coming up with some webinars on that shortly. So let me turn this over to him.
Okay, thanks for the introduction, Chris. Let me start by sharing my screen.
While Anshong's starting to share his screen, I'll also add that you can type in questions on the GoToWebinar interface. There's either a chat window or a questions window, so Anshong will monitor those.
Yep, indeed. I'll keep an eye on the question and chat section. Feel free to post anything during the presentation. So I understand that today's presentation's topic is about ESD electrostatic, indirect electrostatic discharge analysis with HFSS. While what you're seeing on the screen right now, it's a different title. So the reason that I'm using this presentation is that the ESD simulation is part of this EMC simulation in product concepting. So we'll touch on the ESD side while we go through this presentation. So the purpose of this presentation is to kind of address what EMC really is and trying to validate a product concepting through this product. The product we're about to see is a coffee machine. We'll get into details in just a bit. So kind of like the agenda of this entire presentation, we may not touch on every aspect, but our focus will be on the analysis part and the demo and analysis part, and the real software demo part. So firstly, we want to address what is EMC. Also, the second portion will be prototyping and workflow using our ANSYS products. Then we'll follow up with the EMC simulation demo, and then lastly we'll take a look at the results, analyze it. So what EMC really is? So EMC, it's acronym from words electromagnetic compatibility. It means that all electric devices and installations influence each other when devices are interconnected or close to each other. So fully standardized test cases which are able to put on simulation environment. EMC also designates all existing and future techniques and technologies for reducing interference, EMI, and enhancing immunity, RFI. So virtual prototype-based product design workflow is one of the key component in this workflow. So for EMC authority requirement, if the product does not pass the product-specific EMC tests, the device cannot be placed on the market. Hence, that's one of the importance why we address EMC during the simulation stage. As you may know, EMC is divided into two main areas: emission and immunity. So for emission, electromagnetic interference, EMI gives a limits on how much the EOT equipment under test can emit energy out. Electromagnetic susceptibility or radio frequency immunity gives a requirements how immune the EOT should be withheld. These two areas are again divided into two categories: conducted phenomena and radiated phenomena. Typically, projects have in early phase a lot of degree of freedoms in terms of materials, filtering, grounding methods, shielding needs, component placements, mechanical structure, PCB stack-up, etc. So designers they can do early stage risk estimations for new technologies and that way to get early stage information of potential risks in the design. So, so when testing starts when testing starts, many design solutions are freezed, so number of solutions are therefore limited. If product fails in testing phase, a degree of freedoms to solve these fails are quite limited as well. If although also if corrections needed in production phase, solutions are very limited, so very expensive or even impossible to do. So here, so traditional, so under the traditional prototyping, there are some cons. So one would be, first of all, it might be very slow in the traditional prototyping workflow. It might also be expensive way to do products nowadays. With the products are getting more and more complicated, it becomes more expensive to do thorough products. Designers make only reviews, order prototypes, test prototypes, report failures, correct failures, order new prototypes, and so on. So this workflow is requires making prototypes and test the prototypes repeatedly. And by having this workflow, designers can have very many physical prototype around. So virtual prototyping, which can be done in with ANSYS products, there on the other hand, there are a lot of pros. There's a lot of pros doing it as opposed to the traditional prototyping strategy. So one of the pros would be, it reacts fast to challenges, materials, mechanics, and other solutions will be simple to change and check relatively effectively as well. When solutions are found and the backup solutions listed, it is time to order a real prototype. Ordered prototype is much more mature than prototype, which is based to only for reviews. So as you can see, instead of prototype 1, prototype 2 with this repeated cycles, we divide that into a divided into a design feedback loop, and by doing so, we'll just do a EMC simulation 2-3 times, and we can get a first prototype, and then we can have EMC measurement, follow up with the EMC simulation and redesign. Then we can come to the final prototype. Instead of doing prototype 1, 2, 3 iteratively, we only need 2 prototypes. So other words, from 6 real prototype rounds, we can reduce it to only 2 real prototype rounds. So let's take a look at an example of an EMC design workflow. The workflow starts first by planning, of course, intuitively. The designers have some ideas which are collected together, and this starts a planning. After the plan, after the plan is ready to process, it continues to the management mission approval. At this stage, at this phase, industrial designer make first 3D drawings. Also, dimensions, materials, and other features are listed, but not freezed. There could be several different concepts related to materials, colors, so on. So after that, so let's take a product planning. So the example would be a user-friendly IoT coffee machine that has a touch screen control So we're at a planning stage, as if we're trying to design this product, this coffee machine. So some of the specs, so we have talked. So after touch screen control, we also want this to have, say, maybe accurate thermal control for water, water amount metering. At the same time, we want this to have a stylish outlook, metallic body with plastics, and Wi-Fi connection for IoT. So that's the planning stage. So with that, we have uh, now we have a mission approval with with the conditions and the specs listed here. As you can see, this is an ANSYS brand coffee machine, and it does has a stylic outlook. Uh, so let's say the management has done a mission approval. So this will be a ultimate new age multi coffee maker, capacitive touch screen, as we said before, IoT connectivity through WLAN, uh, very accurate water temperature control, accurate water amount meter. So those are all the functionalities, that features that we want this coffee machine to have. um, so after the planning, then we'll go to the concept development. So the first EMC simulation model we'll create from the first mechanical 3D sketch. Then then how do we tell what's a good phase to start virtual tests for EMC solutions? So for example, like how the grounding would affect the performance of the coffee machine, how many grounding points are needed, what kind of voltages can couple from external interference to internal interference, is shielding needed, E and H field hotspots in PCBs which may disturb components in the product. Disturb components in the product. Would that be the case? How materials affects to antenna performance, like, and what about antenna placements, so on. There's a lot of concept needs to be validated. So hence we were at the the concept development stage. Um, then we will going to then we can take a look at a one of the concerns, the concepts we need to address, which is not a topic of today's webinar: indirect electrostatic discharge using ANSYS HFSS. So a standardized the ESD test setup for IEC 61000-4-2. That's a standardized the ESD test. So the graph shown here on this page is the setup, the general setup for this type of test. What this test do is that it would simulate a case where the static discharge hits to the EUT equipment, either directly or indirectly. So the EUT, which is the coffee machine in this case, will be tested by a series of ESD discharges. The post ship is 0.7 nanoseconds time step over a 60 nanoseconds period. The base standards voltage is from plus minus 0.1 100 volts up to plus minus 15 k volts, 15 kilovolts. In automotive environment, this might go up to plus minus 30 kilovolts. So coupling mechanisms, it could be either direct through air discharge, direct through contact discharge, or indirect discharge, which will be vertical coupling plane, or indirect discharge through a horizontal coupling plane. And also to be noticed is that the EUT, the equipment under test, can be damaged in the test. So the idea is, by the EUT, we place a what is that, a coupling plane, and then we put the discharge gun right next to right against the coupling pin to do a indirect discharge. So our the demo that I'm going to have a demo right after this for the coffee machine, and we are only addressing the indirect discharge through a vertical coupling plane in this case. So as I was saying just now, the mechanism is that we put a coupling plane next to the EUT and put the discharge gun against the plane so that it will have the indirect discharge onto the EUT. So a real scenario will look like this. This is a space claim. This is modeled in as a space claim, I believe, and some rendering through a keyshot. So the coffee machine is on the table. We have a vertical plane that has a discharge, electrostatic discharge gun attached to it. Other things needs to be addressed. So we need support. We also need some resistors that touch the ground, and we also need a ground reference plane. So in this case, we have an aluminum sheet placed under the table. We also need a plastic insulator. Uh, where is that plastic insulator? Um, so, so the vertical couple plane is aluminum. On a horizontal plane, there is also aluminum placed underneath the coffee table. Uh, Support of that vertical plane is plastic as well. Underneath the insulator, underneath the in between the horizontal plane and the insulator and the coffee machine, there's a plastic insulator. So yeah, that's the uh, so the graph we're looking at right now, uh, all components in this graph, all components and devices in this image are well standardized. Uh, this is a very simple test to do, but test requires physical prototype. So that is the key. So without making the actual prototype, we can do that in ANSYS. So this will be so right now we're looking at the input voltage at the ESD gun. So this would be the shape of the input voltage, which we'll talk about in just a minute. And then the vertical coupling plane sh shoots electromagnetic uh, uh, shoots would generate an electromagnetic field that interferes with the coffee machine. So the purpose then we'll use a simulation to our HFSS to address this problem. The ESD simulation example in HFSS model would be something look like this. Of course, we omitted the table, but then other key components are all presented here in the GUI. So a close-up look at the machine. As you can see, this will be represented as the tip of the ESD gun. As we mentioned, we have a input voltage shape of on the input gun. So how do we implement that? We simply go to the design data sets and uh, kind of manually, or you can also import data sets if it is available in your Excel sheet or mostly Excel sheets, or you can manually enter those values by hand. Um, Either way works. There is a lot of ways to implement this, but the idea is to have this discrete value, how to say, data points entered. We have enough data points entered to fully represent the input voltage. And then this will be a transient solution with a composite excitation. Uh, for the voltage source, as you can see, we specified that as a function that used the data set of the input voltage that we just entered. The magnitude, we specify the magnitude, and then we can uh, we can have a signal. We can have a signal that's realistic. That's you know, practical and realistic, close to the voltage discharged by the ESD gun. And also we can take a look at the spectrum, the frequency responses of the input. And after the simulation, we can see the animated electric field distribution and as well as indirect discharge. Uh, so on the left side is on the upper left is the vertical coupling plane. On the right upper right, that's the horizontal coupling plane. We have the post chip, which is the input from the ESD gun, and we can see that the internal components, these junctions and the IC boards, I would assume they are indirectly discharged. As you can see at the very beginning, before say 25 nanoseconds, there was a really high discharge. After, as you can see, after 70, right after about 70 nanoseconds, then that uh, that decays down and then comes back up. So there's a little bit more concepts and concerns that needs to be addressed in this product prototyping, but today's topic is mainly just about the ESD. So we can, if any of you guys are interested, I can share some of the contents with you guys, and just to give you a better idea of how that looks like in the actual software instead of just looking at the presentation slides. I'm showing you what it looks like in our HFSS GUI in case you are not our HFSS users yet. Um, so I got this simulation, this original project file this morning. So it is still analyzing. So it's a relatively long simulation. As you can see, it says solving the source ESD with transient solver. Time is at about 9.5, 10 nanoseconds, where the entire simulation goes for 150 nanoseconds. This has been run for about 30 minutes to 1 hour. So we're still not close to the end yet, but we can explore the settings a little bit. So um, let's see. It is let's I will abort this. So during the simulation, you can always abort it. So it is aborted. It will be to be easier for me to drag it and rotate it. Um, so not I'm not very sure where. So as you can see, the cat, the initial cat is imported from outside source. So we don't typically um, model the actual CAD in ADT. Not that we can't. It's just that it's not as powerful as our SCAD tool, which is SpaceClean. Um, so the geometries are imported, and after the import, you can specify the material property. You can specify the materials. This I would say this is a relatively complex simulation. in terms of the model size and the details it involves. So as you can see, there's a lot of excitations. So we have an antenna excitation. That's a lump port, which is at the bottom of the coffee maker. We'll have a second antenna port on probably somewhere on the other side of it. That's there. And we have a CPU, display port 1, 2, 3. We have ESD here, ESD excitation here, and 2 IC ports. And in addition to that, we have a lot of boundaries. So I've never seen this many boundaries in one simulation. And these sheets are specified on the model to either be assigned as a boundary conditions like grounds or are input excitations. So like these ICs or these lump ports. And then the voltage, I believe, is assigned here on the ESD. So we can take a look at the, so far we don't have many results. It only goes to 10 nanoseconds. But as you can see, we can take a look at, say, field strength that between the PCBs. Also, UIFPC connector. Of course, these are not completed. We can also address the display driver area. See, so based on inputs, we can see the interference on the display driver area, the transient field of a transient magnetic field, and lastly the IC outputs. We can also take, as we can see, we can also take a look at the electric field on an XYZ direction, as well as the magnetic field. That's magnetic field is we're only looking at within the coffee machine. And then once the simulation is completed, we can have a animated results. So in conclusion, this would be how it looks like in the HFSS environment. So on the surface, it doesn't look any different from any other simulation, or indeed it is still a simulation. But what we're trying to do is to do a product concepting from the beginning, and then trying to avoid actual prototyping as much as we can. So in this case, we're addressing the ESD. We're addressing the ESD, the electrostatic discharge test. There's, of course, in the industry, engineers, you're all acknowledged and aware that there are many more tests. For example, a couple months ago, we did a circuit simulation for a company that they're trying to pass a military standard for a lightning strike on their device. And based on the results from our simulation, the customer were able to adjust their design or change their designs in the upcoming prototyping. Not that they're trying to avoid prototyping once for all, but before the prototyping, it is always nice to have this simulation, so that we can pass a prototype at once, or I can say as soon as we can. So yeah, that's the idea of using HFSS to do the ESD simulation by reducing prototyping by reducing prototyping duration. And this would be all the contents I have today for you. If you have any questions, or feel free to just type it here in the question sections or the chat section, or raise your hand. I think there is a button for raise hands. Okay, there is a question. Got a question. Is it possible to use Maxwell transient solvers to simulate ESD? I would say that is not impossible. But I'll need to investigate, and I will. So Maxwell doesn't have. So first of all, it's not a high frequency solver. So you can use. So right on top of my head, I think you can still use Maxwell transient, because it's, after all, ESD is just a voltage discharge. So other than that, I don't see any reason you can't. But one disadvantage might be uh, if there's any antennas that's involved in the simulation. I would say it would be still better to go with HFSS. If it is just a pure ESD simulation, then Maxwell should also be fine. Yeah, thanks for the question, Tim. Is there, okay. Um, okay. Seems like that's it. Yeah, if you, as Chris introduced at the beginning, so we have a full library of webinars contents are on our website, and we have a full list of webinars on our website. There is, so that's under resources, webinar library. So we have topics covered for structure, fluids, and as well as electromagnetics. We also have a lot of stuff on this. We also feel free to explore the training and events on our website. We have, as you've heard already, we have webinars almost every Wednesday or every other Wednesday. We have trainings going on. We have training scheduled all through the year, and feel free to explore and sign up for the trainings if that's what you need. And what else do we have? We also have a company conference, upcoming on February 19th next year. Of course, we're sending out more informations and and newsletters to remind you guys to sign up for that. Other than that, that will be all for you guys today. Thanks for your attention. Thanks for joining the webinar today. Have a nice day.